Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 4.1.1, which is Introduction into Factoring Expressions. One of, quite frankly, the most important topics you will ever learn in Integrated 2. This information will definitely carry over into your next math class and even your next couple of math classes. So please make sure we're paying a special importance to this particular chapter here. We will be dealing with quadratics and quadratics galore, and it's going to be a lot of fun. So let's take a look at 4-1 here. It says, review what you know about the products and sums represented by rectangular area models. This is going to be the chapter where all of the area model work that we've been doing will definitely come full force. And we saw some area models and their applications in the probability section a couple chapters ago. But this is definitely where a lot of our area model work is going to come to fruition, and we might even see the return of an old friend at some point in this chapter. So let's see how this goes. Right now, in Part A, they're asking us to examine the algebra tiles at the right, and we have to write an equation that expresses the area as a product equal to being the area as a sum. Okay, so let's just go on and fill in some dimensions here. We got y's up and down this row here. We got x's up and down this column here, and then we've got 1's all the way across here, and an x right there. So if I was to write this as an area as a sum, if we were to do area as a sum, well, that would just be the pieces on the inside all added together. So it looks like we've got 4y's, so 4y plus how many x's? 4, 5, 6 x's, plus looks like 8 of the little guys, plus an xy plus an x squared. And if I wanted to write this as a product, I'd have to notice that this is going to be a value of x, 1, 1, 1, 1. So this in total is going to be x plus, looks like 4. And then this guy right here is going to be y. That's x and then 1, 1. So that's going to be y plus x plus 2 all together. So if I wanted to write this as an area as a product, it would be x plus y plus 2, I just reversed the order here, and then times x plus 4. Now, if I was to multiply this together, I would presumably get this, but let's find out if I do. So let's see. When I do a 2 by 3 like this, it might be easier if I was to do x times x plus y plus 2 plus 4 times x plus y plus 2. It might make it a little easier for me to see that happen. A triple distribution will happen here, x squared plus xy plus 2x plus 4x. I'm going to distribute the second guy here, plus 4y plus 8. Let's see if there's some terms that can be combined out here. I'm looking at that guy, 6x plus 4y plus 8 plus xy plus x squared. And lo and behold, this guy, when we multiply him out, actually becomes this guy, just in a different order, but luckily in addition, order doesn't matter. So that is how we handle areas of product and areas of sum just for our review. And so now we're going to be using algebra tiles to multiply that area as a product together to find out what it looks like as an area as a sum. I don't have the algebra tiles with me, but we can just draw an area model here. And what I can do is I can go ahead and call this 6x minus 1 and 3x plus 2. If I was to multiply them together, I would get 18x squared minus 3x, 12x, and negative 2. Again, I'm just multiplying all the areas together, and if I wrote this as an area as a sum, I would get 18x squared minus 3x plus 12x minus 2. These guys combine out to become 18x squared plus 9x minus 2. And there we go. There's 4-1. I'll be right back with the next couple problems. In 4-2, it says that the process of changing a sum to a product is called factoring. When an expression is written as a product, it is said to be in factored form, and each of the expressions being multiplied is called a factor. And they ask us, can every expression be factored? Basically, what they're trying to tell us is that when you have what's called a trinomial expression, and that's what this is what's known as a trinomial expression. When it's written in this form, And we want to convert this into an area expressed as a product. So this guy times this guy. The process is known as factoring. So what we're going to do is we're going to mess with a little bit of algebra tiles here, and we're going to figure out, can each of these areas as sums be written as an area as a product? So I'll be right back with what the tiles look like. Give me a second. And here we are with how to structure each of these areas as sums into areas as products. And by now you should have been messing with these algebra tiles to kind of get these into a rectangular form. Now again, why was a rectangle so ideal for each of these expressions? It's because the notion of a rectangle's area can be expressed very quickly as a product. So how do I do that? Well, if we look at the rectangle here on the left, the original expression was 2x squared plus 7x plus 6. And what that means is I've got 2 of these x squared tiles, 7 of these x tiles, and 6 of the mini tiles. And the way I express this as an area as a product here will be, let's see, this would be an x and a 2 here. And then this would be, looks like 1x, another x, and then 1, 1, 1. And so how do I reconcile this idea right here? Well, this guy becomes x plus 2 in total. This guy becomes 2x and then plus 3. So if I wanted to write this as an area as a product, it would be 2x plus 3 times x plus 2. And again, the area as a sum would just be all of these guys added up together, which is the original expression. Now for B, I decided to reorient the triangle, the rectangle in a horizontal way, but it doesn't matter. It could have been vertical. I just want to show you that the options exist. Again, how do I write this as an area as a product? It would just be x, x, and x with a 1, 1. So then I end up with 3x plus 2 on bottom, and then x, x, and then 1. So a total of 2x plus 1 up top, and then 2x plus 1 times 3x plus 2 would be then written as an area as a product. So not all of these are going to be factorable, like this guy, C here. It's just not possible, so not possible, and that's no problem with that. And don't worry, there will be a tool that we will learn eventually that will allow us to handle situations like that when they're in an equation, and we will get to that in the next chapter. And then finally, this guy, which seemed really difficult, but we can go and handle him. He's just y plus 3 here, if we kind of speed things up. And this is x and y. So if I was to write this as a product, it would be 2x plus y for the side, and y plus 3 for the base. And so that is writing an area as a sum written as a product. I'll be back with the next set of examples. In problem 4-3, they're asking us to work with our team to write the sum and the product for the following area models. And are there any special strategies that we discovered that can help determine the dimensions of the rectangles? And we have to work to come up with those strategies with our team. And so what I'm going to do here is I'm going to go ahead and say, all right, in order to write this area as a product here, I want to first divvy up this 6x squared here. Now, I have a couple of options. I can call him, because 6 can be divvied up into 3 and 2, I could write a 3x here, and I'll go and write that down here, a 3x and a 2x here. Now, the issue with me doing it this way is that a 2 here is not helpful for a 15 because 2 times this dimension is supposed to get me 15x, but I can't really do that based on what I'm seeing right now. So I think the better option is to put the 3x here and the 2x here. Now, there's also another advantage to doing that, because notice how there's a 2x that exists right here in this box here. I'm going to get rid of this a so it's not confusing. There's a 2x that exists in this box on the top left. And I know that if I just plugged in a 1 right here, I know that a 1 times a 2x would get me 2x. 3 times, looks like 5, would get me 15x. And I believe that is going to get us our area as a product. So 2x plus 5 times 3x plus 1. So there is strategy towards getting these things into their respective places. You definitely want to be able to reverse engineer the individual boxes here. So again, 5xy. look at the box above that. There's a y there. So definitely, I think that the y is going to go here, and the 5x is going to go here. Again, why was the 5x on the side? Well, look at the box to the right side. There's a 15 right there, right? Which means there needs to be some type of 3 in order to turn that into a 15. I'm assuming that's going to be plus because they're both positive. And then this 6 up here, well, this is going to need to be a negative 2 in order to fit the mold of a negative 2y on the left and a negative 6 on the right. So that's going to be y plus 3 times 5x minus 2. Again, you're just reverse engineering the dimensions that would get you the particular area. So in this case, again, look at the 12x squared. We know it's going to be either 3 and 4 or 6 and 2. But look at the diagonal boxes right here. One's a 9, one's a 16. That lets me have reasonable suspicion that we are not dealing with a 6 and a 2. It's very, very likely we're dealing with a 4 on the side and a 3 on the bottom. And so hopefully this idea of looking at the adjacent boxes is helpful in extrapolating the area. I believe that's going to be a 4, and I believe that's going to be a negative 3. And notice how negative 3 times 4 also gets me negative 12. So here we go. 3x plus 4 times 4x minus 3. And I think that will wrap it up for this particular section here. We will go ahead and continue our factoring journey throughout this chapter. So we will learn how to construct these boxes on our own in the next section. So as always, please feel free to leave comments or questions in the comments area, and I will see you all in the next episode.